Hello everyone, welcome to Industrial Electronics Lab number 4. So today's experiment is about 555 timer IC as a Astable Multivibrator. That is part A, and we have to perform the simulation in Proteus. So here is the pinout given. 555 timer, it's a monolithic timer with 8-pin IC. So these are the 8 pins along with their pin functions are given over here. Pin number 1 is the ground, 2 is the trigger, 3 is the output of the pin, 4 is the reset. So it's an active low reset. That means if you apply a high at the reset pin, it will be deactivated. And if you apply a low pulse to a reset pin, it will reset the timer output, or it will deactivate it, whatever is the output currently. So 5 is the control voltage, 6 is the threshold, 7 is the discharge, and 8 is the VCC pin. Now, there are some of the features of 555 timer IC. Basically, it's used to produce a delay anything anywhere from microseconds to around seconds also. And it operates in both astable and monostable mode. Astable will have no stable state. Monostable will have one stable state for the output waveform. It has an adjustable duty cycle. Duty cycle can be adjustable, and it has a high current output which can source up to or sink up to 200 milliamperes of current, and output can drive a TTL value. I mean a TTL logic, and its output can be a normally on or a normally off. Okay, so yeah, so let's get back to the circuit initially quickly. So this is my circuit schematic for a 555 timer, right, as a astable multivibrator. So pin number 4 is connected to VCC. That means it's inactive. Reset pin is inactive. Between pin number, 4 and 8 are together. So between VCC and ground, we have two resistors, RA and RB. Between RA and RB, the pin is connected to, the wire is connected to pin number 7. 2 and 6 are sorted, and that is connected to between RB and C1. The RA, RB, and C1 are the external components. Then at pin number 3, it's the output. We can check the output on the CRO. Between pin number 5 and ground, we have connected 0.01 microfarad capacitor. This is to eliminate any noise present. And pin number 1 is my IC ground, which is connected to a ground. Now let's quickly glance through the output. How does it look like? So over here, we have a capacitor. So we will have a charging and discharging. So while it charges, it can charge max to 2/3 VCC, which is 2/3 of 5 volts over here, which is 3.33 volts, and it can discharge max to 1/3 VCC. That will be 5/3, which will be 1.67 volt. So this is, if you plot the waveforms across the CRO, across the capacitor on the CRO, you will get to see this waveform charging and discharging. Limited, its amplitude is limited to 2/3 VCC and 1/3 VCC. Fine. Whenever the capacitor charges, the output is high and it's equal to 5 volt. And whenever the capacitor discharges, the output remains at low or logic 0, which is 0 volt. Now, the total time period T is a combination of T on and T off. So whenever capacitor is charging, we can note down the T on time or the charging time. And while the capacitor is discharging, we can note down the discharging time or the T off time. So capital T time period will be T on plus T off. Okay, so this is about the waveforms. These waveforms, you will observe it on the CRO in Proteus. Now, let's check various formulas. So T on time, it's given by 0.693 RA plus RB into C1, right? You can read the description. T of time is 0.693 RB into C1. Then we have, this is how we can determine T on and T off. And then we have the total time period of the output, which is T on plus T off. And the frequency will be 1 upon time period. Now, the new concept is about the duty cycle. Now, duty cycle is defined over here as the ratio of on time T on to the total time period, right? So let's say, for example, for a square wave, the duty cycle is 50%. So for this waveform, which you see on your screens, the duty cycle is more than 50% because T on time is greater than your T off time. Fine. So you can calculate your duty cycle in percentage. Now, about the formulas and the circuit diagram and the waveforms. Now it's time to simulate the circuit in Proteus. So let me open Proteus over here. and put the screen in this mode. And let me keep this OneNote also ready over here in the side so that I can refer the circuit diagram. Yeah. So everything is in place now. So let's start building it. So this is my Proteus, design suite 8.10. It's a demonstration version. So go to File and go to New Project. So a wizard will open up. So click on the next. Many times you have to click on the next, and finally you click on the finish. So the moment you click on the finish, a blue square screen will appear. So within that, we have to, put all our components or the devices. Now we have to go to pick devices from here and type 555. As soon as you type 555, you will oversee over here 555 libraries, analog, and timer. Description is a timer. So click on it and click on OK. And you can place this by double clicking on the screen, middle of the screen, and then you can expand the screen by scrolling in and out from the, from your mouse pad. Fine. So now we have added this 555 timer. Next is we want to select, register. So we'll type RES and 0.6 watt metal film registers we can add. And that has been added to the library. Next, we will add capacitor. So we can type cap and here all the capacitors will come. So yeah, we can select this cap device, generic non-electrolytic capacitor from the library and click on OK. Fine with this? So now we are going to place various components. So first of all, we will place connect 8 and 4 towards the VCC, that is 5 volt. So let's start doing that. So this is my generator. So from the generator, select DC. And that DC, you can place it onto the screen like this. Okay. So once you place it, it will be available over here. And now we have to connect it to the pin number 8 and pin number 4 also will be connected over here. Yeah. So it doesn't mean that you have already given 5 volts. You have to double click on it and you can change the name to VCC. And voltage we can give over here as 5 volt. And then click on OK. Don't assume by default it will be 5 volts. You have to double click and set the voltage as 5 volt. Now, so we have powered the IC. Pin number 4 and 8 connections are done. Now we have to connect RA, RB, and C1 capacitor. So again, we'll go to the component mode and select a register. So we can place 2 registers over here, one over here and another over here. And next is we can right click and rotate it clockwise. Again, we can right click on this and rotate it clockwise. Fine. And now we can connect them. This is connected to the VCC register RA. And then these 2 registers are connected to each other. And below that, we have a capacitor. Correct? So let me just drag it out a little. A little bit of, let me select the view screen properly so that I can, yeah. So now we have to select the capacitor and place it over here. And then I'll rotate it clockwise. So this is being connected to pin number 6. And this is connected to the capacitor. Yeah, so the connection is made. And from pin number 7, as you can see on the left hand side, it's connected between register RA and RB. So here is the connection. Okay, now we have to select the ground pin. So from the terminal modes, you select the ground. And you can add your ground over here. And pin number 1 should be connected to the ground. That's the ground pin. Then this capacitor is connected to the ground. So we can connect it to the ground. And then we can change the values. This is RA actually. And its value is how much? 7.2K. This is RB register. And its value is 3.6K. And this is C1. And its value is 0.1 microfarad. Okay. So we have given RA, RB, C1 as external resistors and capacitors and connected to the IC as per the given data. Now, Pin number 2 and 6 are connected together, so we can connect it like this. So you might be thinking, is there a connection between pin number 1 and 2? No. Whenever there is a connection, a dot will appear. So here there is a no connection, so it's a jumper actually. Fine. Now one more capacitor is connected between pin number 5 and ground. So again, we'll go to component mode, select on the capacitor, and we'll add the capacitor over here. We'll right click and rotate clockwise. So here is my capacitor, and this capacitor also goes to the ground. Okay, so let me connect this towards the ground. Okay, fine. Let me try again. Yeah, so this capacitor is connected to eliminate any noise present, and this value is C1, C2 actually. This value is 0.01 microfarad, and then click on OK. So now we are ready to simulate, and only thing left is to connect the CRO. So for connecting the CRO, we have to go to the instruments. From here, we can select the CRO and double click on it to add it onto the screen. Okay, so we can check the output at pin number 3. So pin number 3, I will connect it to channel number 1. So let me do that. So pin number 3, it's been connected to channel A, right? And if you want to check the voltage across the capacitor, we can do that by connecting it to channel number B. Okay, so A is my output and B is my voltage across the capacitor. And we can name this circuit. So you can right click, click on place, click on text, and then I can double click it. I can write it over here, 555 timer as Astable Multivibrator. Fine. And we can increase the font slightly, and we can paste it onto the screen, as you can see. So this is my 555 timer as Astable Multivibrator. Please add your roll number and your name along with your title of your experiment. Fine. So these connections are done now, and now we have to simulate it. So let me put in the full screen mode now. And yeah, so let's go to view, zoom to area, so that only that section is visible. Yeah. So now click on the run the simulation. It will take some time, and soon your CRO waveform will be appearing. Yeah, here it is. As you can see, we have some waveform at channel A, which is yellow color, which is the output, and at channel B, which is blue color, which is the voltage across the capacitor waveform. So we don't require channel C and D. So I'll position them down so that they are not visible on the screen. Similarly, channel D. Fine. So here I have to make the volts per division knob, that is your volts per division yellow color dial, to 1 volt. Similarly, channel B volts per division dial, that is blue color, I'll make it to 0.5. And then according to the waveforms, now I'll reduce the times per division orange color knob over here. Okay, so that it fits the screen. So here it is, and now you see you can position it, right? It is similar to what we have seen over here. Correct. So whenever the capacitor is charging, the output is high, and capacitor is discharging, the output is low. So let's check that. Yeah, it's exactly the way we have been visualizing. So let me increase it to, yeah. So as you can clearly see over here, whenever the capacitor is charging, the output is logic 1, and whenever the capacitor is discharging, the output is logic 0. So now if you want to, output will be TTL compatible, that is 0 to 5 volt only. But yeah, let's check it out. It's amplitude. So I'll place it over here very carefully. Yeah. So counter divisions vertically 1, 2, 3, 4, 5. So V out is 5 divisions into what is the knob at yellow color knob showing 1 volt per division. So this is 1 volt per division into 5 divisions. So that will be 5 volt. Okay. Similarly, you can check whether the capacitor waveform is between 2/3 VCC and 1/3 VCC. Right now, we won't check it. We can check it later. Right now, it's not a requirement over here of ours to check that information. So, I mean, the nature of the waveform is absolutely correct, but we need not check that, verify that 2/3 and 1/3 VCC right now. Right now, we have checked this that the the waveforms are coming properly. So you can take a print screen of this and go to your Word document, and you can add that information over here like this. 555 timer as Astable Multivibrator, and also without the waveforms, that is pause the simulation and then stop it. You can take this print screen also of the circuit. Okay, so first the circuit print screen and then with the waveforms like this it is showing. And now for the sample calculations, for our case we have taken RA as 7.2K, that's a sample value, RB as 3.6K, and C1 as 0.1 microfarad. So those values I have written over here in the Word document. And now using the formula of T on and T off, that is T on will be 0.693 RA plus RB into C1, and T off will be 0.693 RB into C1. Using these formulas, we will calculate it by calculation. First, we'll observe it. Fine. So over here, let me simulate it again. Okay. So we were getting this waveform. Let's concentrate on the output. So let's check the T on time. So T on time or the charging time. As long as the capacitor is charging, it's the on time, right? So let me position it in a way that it's coincide with one of the vertical lines. Yeah. So now we have to count the on time. So it is 1. Horizontally, we have to count 1, 2, 3, 4, 5, 6, 7, and it's around close to 7.5, right? So we have 7.5 divisions into here it is 0.1 millisecond. So 7.5 divisions into 0.1 millisecond. Okay, so that is around 0.75 milliseconds, correct? So by observation, T on time will be, let me just post it on the next screen. So this by observation, T on value is how much it was? 7 point, I mean 1, 2, 3, 4, 5, 6, 7. 7.5 divisions into 0.1 milliseconds, right? So it is 0.7.5 divisions into 0.1 millisecond per division. So this will come out to be 0.75 milliseconds by observation, by simulation. Okay, that's the value of T on we are getting. Now let's check the value of T off. So T off will be, you can check it from here, 1, 2, 2.5. Okay, 1, 2, 2.5. So T off time will be, it's coming as, or discharging time will be, T off is equal to 2.5 divisions into, how much is the times per division knob? Times per division knob right now it has 0.1 milliseconds per division. So we have to enter this value over here, 0.1 millisecond per division. So this multiplication will be 0.25 millisecond by simulation. Okay, so these are the values of T on, T off, and T on, which we are getting by simulation. Okay, for these values of RA and RB. Fine. And yeah, so this you can note it down. For your case, for your case, it will be given to you, RA, RB values given to you. These are just the sample values. Now let's calculate the value of T on by calculation. So it is given by 0.693 RA plus RB into C1. So I will do it in the calculator. 0.693 into RA is 7.2K plus 3.6K, and that is multiplied by C1, which is 0.1 microfarad. So the value which I'm getting by calculation is 0.748 millisecond. Okay, I am getting 0.748 millisecond value. Now similarly, RB T of time will be 0.693 into RB. RB value is 3.6K into 0.1 micro. So that value, it's coming out to be 0.249 748 millisecond. Okay, so here I am getting this by calculation. So this is by calculation. Okay, similarly this value of T of is by calculation. Okay, now the total time period will be T on plus T off, right? So by simulation, the value is coming out to be 0.75 plus 0.25, which is 1 millisecond by simulation. And what is coming by calculation, it is again T on plus T off, which is equal to 0.748 millisecond plus 0.24948 millisecond. That will give you 0.99748 millisecond, and this is coming by calculation. Okay, and you can calculate the frequency by simulation and calculation. I mean, by simulation and calculation. So f is equal to 1 upon t, that is 1 upon millisecond, 1 millisecond. So that will be 1 divided by 1 millisecond. That will be 1 kilohertz by simulation. So this way you can show the calculations, right, for your cases, and by simulation it's coming out to be 1 divided by 0.99748 millisecond, which is equal to, let me calculate, 1 divided by 0.99748 millisecond, that is equal to 1.0025 kilohertz. So by calculation and by simulation, the values are coming quite close by calculation, as you can see. So these are the calculations which you have to do. Okay, T on by calculation, T off by calculation, and then you have to fill up this table. Okay, so for y'all even roll numbers, kindly take the value of RB as 5 kilo ohms, and odd roll numbers, kindly take the value as around 10 kilo ohms, and then C1 value you can take it as around 0.1 microfarad. Fine. RA value, this table will remain the same for all, only RA and RB value will be different for different roll numbers. Then you note down the charging time. Charging time is same as your on time. So this is same as your on time. Okay, this is same as your off time, T of time, and output frequency in hertz. So just now we have shown the calculation for one sample reading for RA equal to 7.2K, RB equal to 3.6K, and C1 equal to 0.1 microfarad. Similar calculations you have to do it for, and for these different values of RA, for 3 different values of RA. So you can take 3 different registers and do it one by one. All the any one sample calculation should be shown in detail for any one of the cases, right? But we have to enter these values in the table. It is given in the write-up in this form only. Fine. So you have to calculate the charging time and on time, discharging time and off time, and the output frequency. Fine. Okay. Now, if anyone is interested, I mean, this is extra. This completes part 1 of the experiment. That is all. You have to just measure the output frequency, discharging time, and the charging time of the output pulse. Okay. Now, if you are interested, now this part is little bit extra, so you need, it's not a part of this experiment. So if you want to know the duty cycle, how will you calculate? Now, this is the output waveform. It's a rectangular wave, right? So if I want to check the duty cycle kitna hai, then what will I do? So what is the duty cycle formula? This is extra. I'm writing over here, not a part of experiment. So percentage duty cycle is given by the formula T on divided by T, total T. So in our case, what are we getting by simulation? By simulation, we are getting the T on value as 0.75 millisecond divided by total time is 1 millisecond into 100. I mean percentage, right? So this number will be T on upon T multiplied by 100. So it will be 0.75 divided by 1 millisecond into 100. And if you do that, you will get 75% duty cycle. Okay, so duty cycle in our case is 75% for this waveform. Okay, similarly for any waveform, if you want to calculate the duty cycle, you have to do it this way. Yeah, sorry for that. Okay. Wait a second. Okay, so the duty cycle of the waveform you see in front of your screen is about 75%. So if you are interested, you can calculate the duty cycle for all the three cases. It's not at all compulsory, but only if you're interested, right? And yeah, one more thing which you can do is we can calculate, earlier, this is also something extra. This is not the part of the experiment, right? So we were talking about whether these waveforms are between 2/3 VCC and 1/3 VCC, right? So we have to check that. Okay, from 0, it will go to 2/3 VCC maximum and 1/3 VCC minimum. That means it will oscillate between 2/3 and 1/3 VCC. In our case, VCC is 5 volt. So it will be 10/3, which is 3.33 and 1.67. So let's check that. So to check the waveform amplitude of the, of the capacitor, right? So we have to, I'll push this channel number A down, and I'll push this, this yellow, blue color waveform exactly positioned at 0. So this is the 0 level, right? And now I will click on DC. So that 0 level disappears, right? So what I will do is I'll keep the, let me keep it DC and ground. So this is my reference level, right? It's very difficult to determine. So here is a reference level near this line, near horizontal line. So let me keep a reference level as this green, just for a reference, okay? Not for anything, any calculation or anything. Let me keep it over here as a reference level, and then I'll count the divisions. Now I'll put this ground to DC. So when I go to DC, I mean this level I want to check, right? So I'll count the divisions now. It will be around 1, 2, 3, 3 point, let's say 4, 3.4 it is. So 3.4 into 0.5 divisions, right? So 3.4 into 0.5, that's 1.7. In reality, it should be lesser than that. Actually, it's 3.3 or 3.4. So we are getting around 1.7 by simulation, by observation. Definitely, we might go wrong in slightly accurately determining that. So actually speaking, it should be 1/3 VCC. So that is 5/3. That is 1.67. But over here, we are measuring it around 1.7. And then continue to measure the peak value over here. So to do that, let me adjust this slightly over here like this. So this will be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 6.6. Okay. So 6.6 into 0.5 volts. So that is coming out to be 3.3. Yeah. And in reality, it's 10/3. 2 into 5 divided by 3, 3.33. And we are getting around 3.3. So this is the way we can check the peak to peak value of the voltage across the capacitor. So that's also extra. It's not required as per se, but I wanted to show you all this. Okay. And yeah, one more fun thing you can do is, instead of connecting a digital oscilloscope, what you can do is, I can pause the simulation and then stop the simulation. Instead of connecting a CRO, just for fun, I can even connect a LED at the output with a series LED. So you can try it on your own. You can connect the LED at the output pin, and in series with that LED, connect a diode. I mean, connect a LED diode. Connect a resistor and an LED in a series combination, and then you can change these values. Right now it is 1 millisecond. So in the LED will be blinking too fast. So you can adjust the values of RA and RB in such a manner that the time period might become in seconds, so that you can visually see it. So you want to do it? So let me do it quickly. So I'll delete this object, and right now I'll go to component modes very quickly, because this is additional part. So I will rotate the register from here and connect it, and I'll go to the component mode. I'll click on red so that I can select red LED. I can type red LED just for demonstration purpose and nothing else. So this is my demonstrable red LED. I can connect it over here, and then from pin number 3, I can make the connections like this towards the ground, just to see whether it's working or no. This will go to the ground terminal. Fine. Just before doing that, this resistance should be very small. Let's say 220 ohms. So this is your series resistance. So I'll call it RS, and I'll change the property of the LED so that it's blinking. So right click on it and change the model type to analog and click on OK. Fine. Now we have to also change the values of RA and RB and C1 so that it becomes in seconds. In second means it has to be multiplied by 10 raised to 3. So what I will do is I will increase the value of RA and RB. This is just for demonstration purpose. Huh? You all don't have to do it. Let me make it 72K and this make it 36K, and C1 value instead of 0.1, I'll take it as 10 microfarad. And so yeah, if I simulate it, yeah, you see it's turning on and off, right? LED is blinking and it's 75% duty cycle, right? This doesn't change. So it's on for 0.75 seconds and it's off for 0.25 seconds. Okay. So this way also you can verify the output. Yeah. So this is all about the part 1 of your experiment. So in your part 1 of your experiment, you have to note down the output waveform and the voltage across the capacitor along with your name and your roll number. And these calculations you have to do it for any one case for RA. RB you have to take it even an on roll number accordingly and fill this table. So this completes part A of your 555 timer as Astable Multivibrator, which we have done simulation in Proteus. Okay, and we have demonstrated just now how we can connect a LED, and the LED can glow for a particular period of time. It will be on and off for a particular period of time. So this is how we can generate the timing delays. So that's all for this section. For part 2 section, refer the next video. So until then, have a good day and thank you.